In this video, we're going to look at resonance structures. They're really awesome. You might hear them referred to as resonance hybrid structures, and in a moment, we'll see why. Let's start by drawing a good example. So let's do the nitrate ion first. We'll follow the localized electron model if possible. So, I don't know, let's follow the rules of LEM. I would have a nitrogen atom in the middle with his 5 valence electrons. So usually looking for 3 bonds, which cool, I've got 3 oxygen, right? Okay, so let's add an oxygen. He's got 2 singles and 2 pairs. Ooh, how's this gonna work out? Are you stuck? I am. I mean, I see that I could like single bond this oxygen. La, la, la. But oxygen needs another bond yet. And I have 2 more oxygen to add that are all going to be in the same boat. Here's a case where LEM fails. Trying to follow the rules doesn't get you anywhere. Sad face for the LEM. LEM, sad face. It's where I start. I honestly always start a Lewis structure by trying to follow the rules. I draw my nitrogen with the pair and 3 singles. I draw my oxygen with 2 pairs and 2 singles. Often that works, just not always. In true covalent bonding, all of the valence electrons can be shared however we need to in order to get full octets. So in that case, when LEM fails, our next thought is to count the valence electrons, and let's just try something. We'll try to distribute those electrons however possible to get full octets for all the atoms. So what do we got here? Nitrogen is going to carry 5 valence electrons, and then oxygen has 6 valence electrons times 3. Okay, so that's 18 and 5 for a total of 23. Ew. Well, that's kind of yucky, because I always think that, the stable electrons should be paired, right? Oh, yeah, that's why it's a -1 charge. Oh, so -1 charge means you get to add 1 more electron. So we're going to add 1 for a total of 24. So we need to come up with a structure that uses 24 electrons and gives all atoms involved a full octet. Because nitrogen and oxygen are in the 2nd energy level. They have to have an octet. So we're not thinking anything funky here. Okay, so now let's look at it a little bit different. Let's just try something. Nitrogen, I don't know, let's just add the oxygen. And I try to add them at these 120-degree angles because I know that if there were 3 bonding regions of electrons, like this dash represents, a bond of electrons, 2 electrons, the negative electrons will repel each other and they'll try to orient themselves as far away as possible. Okay, so now let's go around and give octets. The oxygen would need 6 more. A single bond is 2. And nitrogen right now has 6, so he would need 8. This structure gives everybody an octet. But did I use 24 electrons? 2, 4, 6, 8. Darn it. I got 2 extra. I used 26. But it's not like I can just erase those electrons on nitrogen because he has to have an octet. So in that case, try adding a double bond. A double bond will reduce your electron count by 2. Now, where do you put the double bond? It doesn't matter. So what if we get rid of these electrons on nitrogen, and I don't know, let's make this a double. And then I also need to remove a pair on oxygen so that he has an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Perfect, 24. And everybody's got a full shell of 8, right? Okay, so if this structure was correct, it looks as if one of the oxygen-nitrogen bonds is different than the other two, right? And if that is the case, if one's a double and the other two are singles, you would expect a few things. You would expect the oxygen double bond to maybe have a shorter bond length, because double bonds are usually stronger than single bonds, right? So we would expect that that oxygen-nitrogen double bond would be stronger, so it would have a shorter bond length, and it would have a higher bond energy, right? It takes more energy to break a double bond. That's not the case, though. When you really look at nitrate, all three bonds are exactly the same. They're the same bond length, they're the same bond energy. Why do you have to draw the double bond at that one particular oxygen? Could you do this? What if you did this? And I put the double on the top. La, la, la. And then you can put these pairs wherever you want. Or what if somebody else did this? Single on the top. Pair on the other side. Whoa, this is getting awesome. And then we'll put the extra pairs on this guy. What if you did that? In real life, here's what a resonance structure is. All three of these exist simultaneously. Crazy. We'll put them in brackets to show that they're ions. -1. -1. Resonate. There's a reason why these are called resonance hybrid structures. It's kind of like that extra pair of electrons in the double bond. They resonate amongst all three oxygens in the molecule. So at one moment in time, it may seem as if there's an extra electron pair down here. So it looks kind of like this is a double bond. The next moment in time, that extra electron pair has resonated. Whoa, it's moved up to the top oxygen. And then the next moment in time, again it resonates, that extra pair of electrons. Whoa, now it's down here at this oxygen. So like if we said this was like oxygen A, oxygen B, oxygen C, at any moment in time, if I took a snapshot of this molecule, I could find the extra electron pair on any of those three oxygen atoms. It resonates. It's like those extra electrons can move. So that if I could take a picture at any moment in time, I might find them on a different oxygen. Oxygen A, B, or C. So it's not like I'm just like tilting the molecule. In real life, the true structure of nitrate is like a combination of all three of these. It's kind of as if each nitrogen oxygen is like 1.3 bonds. In real life, they all carry the same bond energy. They have the same bond length because that extra pair of electrons spends an equal amount of time at each of the three different oxygens. So sometimes you'll see all three of these structures drawn, and then there'll be a big arrow, kind of like this, showing that all three exist simultaneously. Now on paper we draw one. You don't always have to draw them all, but we should be aware that we could draw the oxygen double bond at any of those locations, and in real life it oscillates or it resonates amongst all three nitrogen-oxygen bonds. They're all the same bond energy, they're all the same bond length. Now the same thing's going to happen with this carbonate ion. And so again, people will say, hey, why is it a -2 charge? That doesn't make sense if I add up the charges on the periodic table. But now what you're going to find is, in order to draw a proper Lewis structure, like with nitrate, we needed to add one more electron. We couldn't give everybody an octet if we only had 23 valence electrons. We need one more, which is why nitrate's going to bond with something like maybe sodium that has one electron to give. That's where the charge comes from, that technically these polyatomics are covalent compounds, in a sense. We don't call them compounds just because they're not neutral on their own. They need to have those extra electrons in order to be able to give everybody an octet. So carbonate, again, if I try to draw this with the LEM model, it's going to fail, because normally I think of carbon as wanting 4 bonds. So how am I supposed to hook on just 3 oxygen? Now you can always try it. Again, that's where I would try. It's where I always start my Lewis structures. 1, 2, 3, 4. But then pretty quickly I realized, oh, this is going to be a little goofy. Because what are you going to do with all these extra oxygen? You only have 3 oxygen, and somehow you're supposed to give them all octets? If you ever start by doing the proper dot structure and you get stuck, switch to the second option pretty quick, where we're going to count valence electrons. Carbon brings 4, and each of the oxygen have 6. Valence electrons times 3. So that gives me 18 and 4 for a total of 22. Well, I can tell you right now that if you only have 22 electrons to work with, you will not be able to give carbon and oxygen an octet. And they need octets. They're only in the second energy level, so they can't do anything crazy and take more. That's why there's a -2 charge. That -2 charge means we get to add 2 more electrons for a total of 24. So we get to use 24 valence electrons and distribute them so that everybody gets an octet. So these structures look very similar, where you're going to have something kind of like this. Carbon in the center. And again, you could try, single bonds, double bonds, but you're going to find that it looks very similar to the nitrate ion. But I wanted to draw both of them so that you've got both of them in your study guide, because these are really common. And then one of them is going to have to be a double. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then we should put the charge on the outside of the brackets. This is only possible with the addition of 2 more electrons. So again, in real life, if I draw that on paper, it looks like I have a double bond and 2 singles. And here with the carbonate ion, they actually give me some data. A carbon-oxygen double bond and a carbon-oxygen single bond. Here are their bond lengths, and it's what I would expect. A double bond is a stronger bond, so it should have a shorter bond length, which it does. But that's not the case in carbonate. In carbonate, all 3 bonds are exactly the same. They all have a bond length of about 136 picometers. That's because it's a resonance structure. It's not that this double bond is only in one location. Let's say this is oxygen A, B, and C again. C. It's not like one of these bonds is different than the other. That double bond resonates. There are 2 extra electrons, and they resonate amongst all 3 oxygen. So at one moment in time, The extra electron pairs are on oxygen A. If you had a fancy camera, the next moment in time, they might be up top on oxygen B. Da, 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 da. And then we add all the dots. And again, don't leave off these dots. As annoying as they kind of are, you have to put them on there to prove that everybody has an octet. The next moment in time, the double bond could be in the opposite corner on oxygen C. And there we go. So here's my single bonded oxygens on paper. Cool. And I'll put the brackets to show it's an ion. In real life, you might see all three structures drawn with this arrow between them, showing that they exist simultaneously. This double bond resonates amongst all the oxygen-carbon bonds. On paper, we got to draw it someplace. I mean, on paper, how do you show that really they're all like 1.3 bonds? Like the bond length is kind of a combo of the oxygen double and the oxygen single bond. On paper, how do you do that? So often they might have all three drawn with arrows between them to show that they all exist simultaneously. That's again why sometimes it's called a resonance hybrid structure. The true structure is like a hybrid of all three of these, where that double bond resonates amongst the different oxygens. So again, they could ask you like, hey, draw an acceptable Lewis structure for the carbonate ion. And any of these would be an acceptable Lewis structure. You follow the two rules. Everybody's got an octet. You use the correct amount of electrons. Then they might give you data like this. And they might say, hey, a real carbon-oxygen single bond has this bond length. And here's the bond length of a real carbon-oxygen double. Why is it different in carbonate? All three, we should add that in, all three carbon-oxygen bonds have the exact same bond length, and they have the same bond energy. That would be another thing they could use. Bond energy, the energy required to break the bond. Double bonds require more energy to break than a single, but in carbonate, they're all the same. They have the exact same bond length and same bond energy, because it's really a hybrid. That extra pair of electrons spends an equal amount of time at each of the three oxygens. So they might ask you to rationalize that. Hey, why is the bond length in carbonate different? It's not that there's one that's a single or two singles and one double. Why are they all the same? And then we'd say, well, really, this is a hybrid structure. And then I'd go on and explain what that means. Another option, O3. Let's draw ozone, and then we'll call it a day. This one's kind of fun. They might ask you to draw, an acceptable structure, or maybe they'll say draw two acceptable structures when more than one might exist. O3, really? Ozone. Normally, when I think about oxygen, I think of them kind of going for two bonds. Something kind of like this. So right away, I'm kind of stuck. If I want to follow LEM, the localized electron model, I don't know where to put three oxygens. So let's abandon that. Into the toilet you go, and let's just go straight to adding up valence electrons. Oxygen has 6 valence electrons. There are 3 of them for a total of 18. And it's neutral, so I don't have to worry about adding or removing electrons. Okay, so let's just try something. I don't know. I usually start with singles. So let's just go around and give them all an octet. Oxygen cannot take an extended. So again, I'm not trying anything fishy here. Cool. On paper, that's starting to look pretty good, right? Everybody's got an octet. They need an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. Whoa. 20. I use 20 electrons. That's too much. That is not an acceptable structure. So often they'll say, like, draw 2 valid Lewis structures or something like that. Well, we gave them octets, but we did not use the correct amount of electrons. This would not be valid. Don't do that one. Now, you might have that, and then you say, oh, that's not going to work out. So clearly cross it off. Now, we kind of mentioned that if you have too many electrons, adding a double bond will reduce that by 2. Where do you put it? Wherever you want. I don't know. Let's go double single. That's cute. Okay, let's give him octets. In the center, this guy's already got 2, 4, 6. There's 8. 2, 4, 6, 8. 4, 6, 8, 10, 12, 14, 16, 18. There it is. There's the correct Lewis structure for ozone. Again, in true covalent bonding, we share all the valence electrons. So it's like a party, and they all come and dump their valence electrons, and then they can distribute them however they need to so that everybody gets a full octet. That's where the localized electron model kind of fails. Because it would be hard to predict this structure if you were like dead set on only giving oxygen like 2 pairs and 2 singles. Okay, so now here's the resonance part. It looks as if there are 2 different kinds of bonds. It looks as if there's a single and a double. So that double bond should technically have like a stronger bond energy, a shorter bond length, and it doesn't. In real life, both oxygen-oxygen bonds have the exact same bond energy and the exact same bond length because it's a resonance structure. So this structure resonates with this structure. Just the mirror image in this case. And we'll add the little dots. You got to add the dots to prove that everybody has an octet. So again, I know it's kind of annoying to add dots all over the place, but you got to do it. These structures resonate. So if I had a fancy camera at one moment in time, it might look as though the double bond is in this position. So maybe, again, we could call this like oxygen A, oxygen B, oxygen C. But really, it flip-flops, or it resonates. So another moment in time, it's over on this side. The extra pair of electrons is over on the opposite oxygen. The true structure is really like a combination or a hybrid of both of these. Again, on paper, if you drew one of them, it would be acceptable. But then if they said, why are both oxygen-oxygen bonds carrying the same bond energy and the same bond length? Then you would go on to explain, ooh, this must be a resonance structure. That the double bond really does resonate. That extra electron pair spends an equal amount of time on both oxygens. So technically it's like each bond is like a 1.5 bonds. But again, how do you draw that on paper? Other things to be aware of. If you would have tried some other options, just while I'm thinking about it, like what if you would have tried something like this? Things to just keep your eye open for. That looks pretty cute because I know like carbon dioxide kind of looks similar. So you got to go around and add all your electrons, give them full octets. Ooh, that guy in the middle already has an octet. 2, 4, 6, 8, 10, 12, 14, whoop. 16, that's wrong. Yeah, just keep your eye open for stuff like that people will draw. Or again, this could be like a multiple choice question, and they might say like A, B, C, D. Which of the following is an acceptable Lewis structure for the ozone molecule? And you look at that, and you're like, yeah, that kind of looks cute. It's nice and symmetrical, and and it looks a lot like carbon dioxide. Everybody's got an octet. So they might trick you and be like, all of the above. Ooh, but there's another rule to correct Lewis structures, and that's that you only have a certain amount of valence electrons to play with. So if it doesn't have the same amount of electrons, like the correct amount of electrons, 18 in this case, that's not an acceptable Lewis structure. So you could find lots of structures that may give octets, but they don't use the right amount of valence electrons. Keep your eye open for that type of a multiple choice question. That sometimes tricks people. They'll pick like all the above or something. But these resonance structures aren't meant to be too crazy, and these are all really good examples. They're really common examples. So I would be familiar with some of these guys. And again, don't let the Lewis structure get the best of you. Sometimes people say, I just can't even get it started. Try the dot structure first. And if that doesn't seem to be working for you, quickly start adding up the valence electrons and draw something. Try doubles, try singles, try whatever you want. Give them octets. If you've got extra electrons and somebody that can take an extended octet, go for it. And then count the valence electrons and see if you use the correct amount. And that should usually lead you to an acceptable Lewis structure.